Hello, hello, hello. In this worked example, we're going to consider a problem from classical electricity and magnetism. We mentioned this because even though this is a quantum mechanics course, we're going to be dealing a lot with the polarization state of photons, and it's good to remind ourselves about how polarized light behaves classically. And so in this problem, we're going to have a beam of left circularly polarized light incident on a linear polarizer. And the transmission axis of the linear polarizer is going to be oriented in the horizontal direction. And the question is, what happens to the average intensity of the beam? How is it changed by its interaction with a linear polarizer? And by intensity, we mean the power per unit area incident, say, on a detector. And when we talk about average intensity, we're talking about a time average. So particularly with optical light, the actual intensity is fluctuating very, very quickly. And what we measure experimentally with a photodetector is the time average value of the intensity. And classical electricity and magnetism tells us that for any beam of light, the way we calculate the average intensity is to take the speed of light, multiply it by epsilon naught, the permittivity of free space, and then the intensity depends on the magnitude of the electric field in the wave squared. And these angle brackets here denote that we're taking a time average value of that of the magnitude of the electric field squared. Now, if you read through the polarization tutorial, you'll see that we would represent a left circularly polarized light beam, the electric field of it, and in the tutorial you use these complex mathematics to represent the electric field of our electromagnetic waves, with the understanding that at the end of the day, the actual electric field is obtained by taking the real part of these quantities. So the left circularly polarized light using the complex exponentials is represented by this expression here. The amplitude of the wave we're calling E naught, and then it's a plane wave, e to the ik is e minus omega t, and then the vector part of it is x hat plus I y hat. And this I just says that is indicative of the fact that there's a 90-degree phase difference between the x component of the electric field and the y component of the electric field. And if we make use of Euler's formula here, we can easily show that when you take the real part, you end up with an electric field that's given by this expression here. And of course, if we're trying to evaluate the magnitude of a vector squared, the magnitude of any vector squared is the sum of the squares of its components. So we're going to take the x component of this vector and square it, and add to that the square of the y component of the vector. And we're going to evaluate this quantity. It doesn't really matter what value of z you pick, but it's convenient to pick z equals 0. So when we go to figure out the magnitude of the electric field at z equals 0, the magnitude of that electric field squared is just going to be E naught squared times a cosine squared term plus a sine squared term here, where it's cosine squared omega t plus sine squared omega t. And now we've got to take the time average value of that quantity. Well, that's easy because cosine squared omega t plus sine squared omega t at any time t is just 1. So our left circularly polarized light has an average intensity that's related to the amplitude of the electric field by this simple relationship, C epsilon naught. So that's our expression for the average intensity of the left circularly polarized light before it enters the linear polarizer. What about after the linear polarizer? Well, the linear polarizer, we're told, is oriented in the horizontal direction. The transmission axis is along the horizontal direction. So the way linear polarizers work is only the x component of the electric field is going to survive. The Y component is going to get absorbed. So the electric field after the beam has passed through the linear polarizer is just E naught cos times kz minus omega t along the x hat direction. So the magnitude of the electric field squared is just going to be E naught squared times cosine squared omega t, where again we're evaluating it at a particular z equals 0. And now when we go to take the time average value of this quantity, well, E naught squared obviously is a constant, so we can pull that out of the time average. And then all you have to know is that when you take the time average value of cosine squared omega t, that's just equal to 1/2. So we conclude that after this beam has passed through the linear polarizer, the average intensity of the beam is now 1/2 times C epsilon naught E naught squared. So comparing this expression with this expression, we see that the effect of the linear polarizer is to reduce the average intensity of the beam by a factor of 2, which is the question that we were asked to answer. So that's our answer. It's reduced by a factor of 2. And that's it for this worked example. Hope to see you again soon. Bye-bye.